Hi, this is continuation for power electronics, and today we are going to cover tutorial session. And the tutorial is a problem set that we are going to solve together and discuss some questions. And we have in this session some questions about calculating the switching and conduction losses for some different circuits. The main objective in this tutorial is to understand, not to know how to solve the question, because I can manipulate the question a little bit and add some diodes or change the shape of the circuit, and the solution will be totally different. So understanding is the main thing that you have to focus on in this tutorial session. So let's start with problem number 1. So we have here a BJT switch operating at 20 kilohertz. So this now transistor is switching and getting PWM with frequency 20 kilohertz with the characteristics shown below, which are these characteristics here. Okay, so it switches 100 ohm load, which is this one. Okay, let's now write here. So there is 100 ohm load and the frequency is 20 kilohertz. Okay, and the across a DC voltage supply, which is 350. So Vs equals 350 volt, which is this one, 350 volt. Okay, and the duty cycle is 50%. So that means delta equals 0.5. By neglecting the base drive losses means these losses here, because that pushes some current to the base, we will ignore these currents that makes the driving losses. And so the ignorance will be for base drive losses. And so we want to calculate the total losses in the switch. Total losses means P losses equals the switching losses and the conduction losses. Okay? And also the thermal resistance of the heatsink required to maintain device case temperature to below 80 degrees. So we have the TC should be 80 degree and the ambient T ambient equals 20 degree. Okay, so here's the question, and we are going to calculate the switching and conduction losses. Remember, the switching losses is known as the on-time switching losses and off-time switching losses, and we have two different equations for inductive load and for resistive load. So we have to choose between these two equations. The second thing, the conduction losses. We assume in the off time there is no conduction and it's zero. But if you are given leakage current information, so you have to calculate also the conduction losses in the off time by using the leakage current. So now let's see the first thing. We have here resistive load. And that resistive load means we are going to get this switching equation, which is 1/6, okay, multiplied by V max times I max times the frequency times the switching on plus the switching off times. Okay, so this is the equation for the switching losses, and this is this includes the on switching losses and off switching losses, and the derivation for that is included in the lecture. Okay, so I think we know Vmax. I think Vmax is the off time voltage, which is 350. So that equals 350 times Imax, which is the current going through that transistor if it's fully conducting. And in this case, we will assume that the voltage drop across that transistor is very small. Okay, so we know the VCE max is 0.5 here, but we will assume it's 0 just to make the calculation simple. Okay, so what is the current going through the transistor if we turn it on completely? I think it's the voltage divided by the resistance, okay, in the way. And the voltage here we have 350, so the current equals 350 volt divided by the resistance, which is 100, and that will give 3.5 ampere. Okay, so we have a 3.5 times we have the frequency, which is 20 kilohertz, times the turn on and turn off time. They are included here. So 1 micro plus 1.2 micro, 1 micro plus 1.2 microsecond, and that will be divided by 6. Okay, we have one transistor, that means this will be calculated just one time. Okay, so what is the answer after using your calculator? And you have to also use your calculator with me, and the answer will be 8.98 watt. Okay, so this is how we calculate the first question. And now let's go to the conduction. Okay, so the conduction, now we have conduction for the on state. Do we have any information about the off state? Let's go up and see. Yes, we find information about the leakage current. So that means we have to calculate the conduction also during the off time, even if it's small, but giving us this information, that means the question is expecting to calculate that one. Okay, so we have P conduction during the off state as well. Okay, so what is the conduction losses? We know this is NPN transistor, VGT transistor, and it has VCE sat, and the information about the calculating the power losses is VCE sat times the average current. So VCE sat times I average. Okay, but what is I average? We know we are switching the transistor by a duty cycle, and we know the I average equals I max times delta. Okay, this is I average. So I max equals 3.5, which is this one, times delta, which is 0.5. It's known here. Okay, so that's why now we have this information. So VCE sat equals 0.5, which is this one. Okay, multiplied by 3.5 amp multiplied by 0.5, and that will equal the 0.875 watt. Okay, so this is the conduction in the on state, but in the off state we have to think about this. Off state, the switch, the transistor is off. That means the voltage applied across its terminals is the maximum voltage, which is the source voltage. Okay, between that point here and that point we have the 350 is waiting there because the transistor is off. So that 350, there is some leakage current going through the transistor, and that leakage current is about, as mentioned here, is 800 microamp. So again, we have to calculate that by V off times IC leakage. Okay, but that should be average as well, because the leakage is not continuous all the time. We are chopping that by duty cycle, so we have to consider the average one. So we have 350 volt times 800 microamp times the duty cycle 0.5. Okay, because the off time is 0.5, not because the duty cycle is off time. Okay, so that one, just to make sure that you understand it, is IC times 1 minus delta. So if delta, the original delta, is 0.7, for example, so this one should be multiplied by 0.3, because the off state is 0.3 from the total duty cycle. But now, because this question has 0.5 on and 0.5 off, so we will take as 0.5. Okay, so the answer will be 0.14 watt. Okay, so we have here the first switching losses and the on conduction losses and the off conduction losses. All of them should be just summed up. So we have the first one and second one and third one, and all of them will be 10 watt. Okay, so this is the answer for the first question. And the second branch is what and the thermal resistance of the heatsink required to maintain the case temperature below 80 degrees. So I know the thermal resistance equals the difference in temperature you want to maintain between, okay, divided by the power dissipation, the total power dissipation or losses. And the question says we have ambient temperature 20, and once you start switching your MOSFET or your transistor, this will dissipate power and that will be converted to heat. Now the temperature will increase, but we want to use heatsink to dissipate that and don't exceed the 80 degree. So how we do that? We have to choose a heatsink that can take all the temperature, okay, and dissipate it very fastly. And to do that, we have to know what is the difference in the temperature we want to achieve for that power dissipation. So we know the power dissipation totally, which is 10 watts here, and we know the difference. We have 20 degree, and we don't want to pass or to exceed the 80 degree. So this is the range of our difference, and we have 10 watt, and that will give you 60 divided by 10. That means 6 Celsius per watt. So our heatsink will increase 6 degrees for each watt power dissipation, and we can choose less than this, for example 5 or 4 if we want, okay, but not more than this to achieve the 80 degree as maximum, okay. So we can choose 6 or less than 6. I think here we have finished problem number 1. So now let's go to problem number 2. So we have here a BGT transistor switching at 9 kilohertz. So this is the first information about the frequency equals 9 kilohertz. Okay, and that's switching an inductive load across the DC supply, and that supply is 200 volt, which is very important to know. So the voltage of the supply is 200 volt, and it's switching inductive load. And we have two types of inductive load, maybe lightly inductive load and heavily inductive load. If it says heavily inductive load, that means we can model it as current source. We will see what the question says later. So with a duty cycle of 40%, so delta equals 40%. The inductive load now is modeled by a current source of 6 amp, and that's said clearly in the question because it assumes that it's heavily inductive load. That means that now inductive load is trying to maintain the value of the current inside it, okay, to be 6 amp. That's why they have modeled it by a current source like this. If it's slightly inductive load, so that the behavior will be different, but assuming it's heavily inductive load will make it easier for us, okay? So now I load or I out equals 6 amp. What's the benefit of knowing I out, which is the load or inductive current here? Because that 6 amp sometimes will go through the transistor like this, and sometimes will go through the diode. So we know what is the value of that current going through the transistor or going through the diode, okay, during switching on and off. Now a freewheeling diode is connected in parallel with the load. I think we know the diode, this one, okay, and the circuit schematic and devices characteristics are below, which are these, okay. Calculate the conduction losses of the freewheeling diode, just the diode, conduction losses for the diode. We have switching losses for the diode, but we didn't cover that because usually we ignore this, okay. But for the conduction losses, it's much more, and we have to consider it. So the question is about conduction losses for the diode, and the conduction losses for the diode means that we have to know the voltage drop and also the average current going through that. However, if you looked at the data given here for the diode, it gives here information about the resistance during the on time. Why I say during the on time? Because it's RF. RF means R forward bias, okay? So if it gives us the resistance, that means I have to consider it in the calculation of the conduction, because the current going through the diode and its resistance as well. Okay, so now let's now write the equation for the conduction. Now conduction for the diode equals the voltage forward for the diode times the average current for the diode, okay, plus the RF, the resistance for that diode, times I square R Ms for the diode. Because when we calculate the power dissipation, we multiply I average times V, which is constant, VF, and for the resistance, we multiply the resistance by I square RMS, okay, not the average value. And we know that from the previous lecture. Now we have to calculate the I average and IRMS because other information are known, okay? We know that I average through any component is the current going through that component time the multiplied by the on time for that current, okay? But now let's think about the on time. We have a duty cycle here of about 40%. Is that 40% for the diode or for the transistor? And if the transistor has the 40%, is it sharing that with the diode or no? Let's now see and look at the circuit and decide what is wrong and what is right. Now this current is going through is coming from the inductor and going to this node. And if the transistor is switching on, that current will go through the transistor during that duty cycle, which is 40% of the frequency, which is 9 kilohertz, okay? And during switching on that transistor, this node here, okay, will be close to 0. That means the diode will be off. So if the transistor is on and conducting, the diode will be off. Now, if we switch off our transistor, now this current, okay, will not go to the transistor, it will go through the diode. And now that the diode will turn on. So the turn on time for the diode is not the 40%, is the complement for the 40%, which is the 60%. So now we have delta. This is for the transistor. And we have 1 minus delta. This is for the diode. So this is the on time for each. And this is very, very important because some students, they just take the same duty cycle and multiply it for any average current, okay? Which is wrong. You have to know what is the on time for that component, and that on time define for you the average and RMS current, okay? So when I want to calculate now the average current, I average equals the I max times the on time, and the on time is 1 minus delta, not the delta itself, okay? And for the current, for the RMS value, it's I max multiplied by square root of 1 minus delta, which is the on time, okay? So I max is 6 amp times 1 minus 0.4, and the second one is 6 amp multiplied by square root of 1 minus 0.4. And RMS will be 4.65 amp, okay? So now let's go back to our equation, which is this one, and calculate the conduction losses. So the conduction losses again equals VF, which is the forward voltage, is 0.3 here, 0.3 times the I average, 3.6, plus 10 milliohm, okay, times IRMS square, which is 4.65 square, okay, and that will equal 1.296 watt. So this is the conduction power dissipation for the diode. Let's go now to problem number 3. We are given the switching time of PGT below are the rise time and fall time as 1 microsecond and 2 microseconds for each of these 4 switches. So the rise time here equals 1 microsecond, and also the fall time equals 2 microsecond. Okay, if we are given the delay time and storage time, so we can also combine them to calculate the turn on time and turn off time. If we are not given that, so we will assume that the turn on time is the rise time and the turn off time is the fall time for resistive load. Okay, now if the inverter was to produce 6 kilohertz square wave output, so the frequency here equals 6 kilohertz, and neglect the power dissipated in the base of the IGBT and the offset losses. That means if the transistor is off, so there is no leakage current, so we will forget this. And also for this base, we have also some currents injected to the base here, and the question asks us to just forget it or ignore these losses. Okay, so we will assume that the losses just during the on time and off time between the collector and emitter and the flowing of that current. Okay, calculate first the total losses in the bridge switching devices. When the question asks about this, that means all the switches, the transistors and the diodes, because the diodes are switches as well. Now remember, we have here in a resistive load. Okay, and the resistive load, that means it accepts any change in current and direction and value. Okay, so what is the pattern for switching this inverter? We switch Q1 and the Q4 together. So that means Q1 and the Q4, they are switched together, and then Q2 and then Q2 and the Q3 also together. Okay, so when we switch on, so that's transistor number 1, okay, will switch on, and the current will go through the resistor like this, and switch 4 will switch on, and that's it. We complete the circuit. Okay, and the output will be positive here and negative there, and it gives us the current that will go through that resistive, because the value of that resistor is not given in the question, so it gives us the current, but the direction can change because it's resistive load. Now when we go to the second pattern here, switch number 2 and 3, so they will switch on and the current will go through Q3 and in the reverse direction and then through Q2. Okay, so this is how the current will go through this circuit. Now it tells us what is the total losses in the bridge switching devices. Now, is there any problem for switching this resistive load? The answer is no, because it accepts any change in current. So if you stop Q1 and the Q4, okay, so the current will stop immediately. It's not that like the inductive load, it has to go and continuously go through the diodes. So now the question is, are the diodes will be conducting any current during switching on and off the transistors? The answer is no, because the current will stop once I stop the transistors Q1, Q4 or Q3, Q2. Okay, so no conduction through the diodes because it's resistive load. Okay, that means the power loss for the diodes equal 0 watt because it's resistive load. If it's inductive load, the inductor doesn't stop the current even if you switch off the transistors, as we explained in the lecture, and you have to flow that current through the diodes, and that's why we have to calculate the conduction losses for the diodes. But now there is no conduction losses for the diode. Now all the losses will be just for the transistors. So we have 4 transistors. If we calculate for one, it will be for also others. Let's go for the power loss for the transistors. Okay, and that means the switching losses and also the conduction losses. Okay, so what is the switching losses now? We have 4 transistors, so I will multiply it by 4. This is for 4 transistors times, okay, for each one we have resistive load. That means we divided by 6. So what is the Vmax for this transistor? it will be the 300, which is this one. Okay, so 300 volt times what is the I max going through the transistor. I think we are given this 10 ampere here, so it will be 10 ampere times the frequency. I think you remember the equation for P switching. The frequency is 6 kilohertz. Okay, times the turn on plus turn off time, which are the rise time and fall time, 1 micro and 2 micro. Okay, and that will give us value of 36 watt. Okay, this is for the 4 switches. Okay, now for the conduction losses, we have also 4 times. For each one, we have the VCE sat, which is the VCE sat, which is the 2 voltage here. Okay, so 2 volt times the I average. What is the I average for each transistor? Remember, Q1 and the Q4 will be switching on according the duty cycle, okay, which is delta, and the Q2 and the Q3 will be switching to the complement of the duty cycle, which is 1 minus delta. But now there is no delta mentioned in the question. It says here square wave. That means delta and 1 minus delta will be 50%. So this one will be 0.5 and this one will be 0.5. But if we have different information, like for example 30% delta or duty cycle, that means Q1 and the Q4, the delta for them will be 30%, and the Q2 and the Q3 will be 70%. And you have to calculate each one differently. Okay, so now the conduction losses will be 2 volt times I average. I average, that means I max, which is 10 amp, times the duty cycle for each, which is 50%. Okay, and this will equal 40 watt. Okay, so the total losses will equal 36 plus 40, and that will equal 76 watt. Now the second requirement here, or the second question, is the thermal resistance of the required heatsink. Once you have this question, just write the thermal resistance equals the difference in temperature divided by power dissipation. I think we know the power dissipation, which is 76 watt. What is the difference of temperature we want to maintain? It says here the maximum device temperature is 60, so we shouldn't exceed 60, and we have the ambient as 20. Once we try to dissipate that power, the case temperature will increase 21, 22, 23, 24, okay, from the ambient, and we have to limit that to not go to 60. So that's why we have to choose heatsink, and that heatsink should take that heat and dissipate it to the ambient very quickly. And to know what is the thermal resistance for that heatsink, so we look at the difference, okay, which is 40 divided by 76, and that will give us 0.52 Celsius per watt. Okay, so I can choose 0.52, 0.5, 0.4. That means for each watt dissipation, just 0.5 degree increase in temperature is seen. And now the third question is, what is the average voltage across the load? Okay, so I think let's now draw the waveform of the load voltage. So this is the time and this is the voltage. Okay, the question already said that it will be square wave, but we want to see the value of that square wave. Okay, so during the on time we have Q1 and Q4, okay, give us the conduction, okay, conducts the current, and it will be in that direction. So the positive will be here and negative there, so it will be 300. Okay, I will ignore the 2 volt VCE sat just for simplicity, and this will be for 50% of the duty cycle, okay, or of the duration. And now after we finish the on time, okay, the Q3 now and the Q4 will Q2 will come now on, and now the current will go just in reverse direction, giving us the positive and negative here. Okay, that means it will reverse the direction like this, like this. So this one is minus 300. volt. Okay, what is the average voltage for this waveform? I think you can go back to our lectures and look at the waveforms and how we calculate the Irms value and average value. I think that was in the first lectures. Okay, and you will find that the average value equals I peak multiplied by 2 delta minus 1. Okay, if you use that equation, you will come up with 0 volt average. Second thing, I think if you look at the area here and area here, I think it will be 0 because they are symmetric. Okay, so in both ways you will get 0 volt average, but the Irms value, no, it has some value which is 300 volt.